We are putting a timetable from 2 to 3 p.m. today, embedded system class, 3 p.m. to 4 p.m. this class. So we are scheduling in terms of hours. Similarly, the microprocessor tasks has to be scheduled in nanoseconds, microseconds, and milliseconds. So scheduling the job and to monitor whether the job is being completed within the time duration or not. For that, the timers are also very much helpful. So now we are going to look at timers in ARM LPC2148 microcontroller. So the objective is to make use of on-chip timers for producing necessary time delay in microseconds, milliseconds, etc. And the applications which demand timers are, and the first example for the UART serial communication with 9600 baud rate, it will take up to 104 microseconds to shift out one bit. So if your peripheral or if your microcontroller is communicating with another microcontroller through UART means with a baud rate of 9600 means, so 1 by 9600, so it will take around 104 microseconds to shift out one bit. So there is a need for a timer to say that 104 microsecond is over, you can shift out the next bit. So the paralleling serial out shift register of a UART needs the timer's help to know that 104 microsecond is over, we have to shift out next bit. So the last column, if you see, for a communication with 9600 baud rate, 104 microsecond is notified by timers. That is the message that we get from this first example, which justifies the need of timer. Then you take the second example with respect to NTSC standard, CCAM standard, and PAL standard. So in 1 second, if 50 frames need to be refreshed means it will take 20 milliseconds to refresh one frame. So every 20 milliseconds, one frame has to be refreshed in our monitors as well as in the TV as well as in the mobile phone screen. So to notify 20 milliseconds is over, there is a need for a timer. Okay, so for video also there is a need for timer. And the third beautiful example that what we are coming across here is for a speech signal processing or for a speech signal sampling, the microphone need to take one sample once in 125 microsecond. So every 125 microsecond, you have to take one sample. So at the end of 1 second, you will get 8000 samples to notify the ADC. So definitely there is a need for a timer. So wherever there is a video, there is a need for screen refreshing for the 20 millisecond time delay is necessary. Wherever there is an audio, 125 microsecond speech signal sampling is necessary. So the notify 125 microsecond is over, we need a timer. And for a serial communication, we need timer. So these three examples justify the need for a timer. And if there is no timer, there is no video, there is no audio, there is no communication. So that is the conclusion of this slide. So this is the block diagram of LPC2148 microcontroller, as we all know. So here we have a timer module inside the LPC2148 microcontroller, which is being highlighted. So there are two timers, timer 0 and timer 1 in LPC2148 microcontroller. So these timers or counters have additional features like capture compare modules, which will be discussed in detail in this presentation. Okay, so normally we know about timer, which is meant for producing time delay. There is something like capture module, or there is something like compare module, which are the extensions of timers. First of all, we are interested to know what is the prescaler. So a 32-bit timer or counter with a programmable 32-bit prescaler is available in LPC2148 microcontroller. So it is mandatory for us to know what is prescaler. Scaling means dividing. Prescaling means dividing before the counting. Okay, before your timer starts counting, dividing the clock pulses is called as prescaling. Say for example, if 1-bit prescaler means it is divided by 2 counter. If it is 2-bit prescaler means it is divided by 4 counter. If it is 3-bit prescaler means it is divided by 8 counter. 4-bit prescaler means it is divided by 16 counter. 5-bit prescaler means it is divided by 32 counter. Similarly, if it is 8-bit prescaler means you can say it is divided by 256 counter. If it is a 16-bit prescaler means you can say divided by 60,536 counter. Similarly, if it is a 32-bit prescaler, means it is divided by 429 crore counter. Prescaler block with respect to LPC2148 microcontroller is shown here, as you see here in the screen. So there are two registers associated with prescaler. One is prescaler register. There is a prescaler counter which starts from 0, goes up to prescaler register value. Whenever it reaches prescaler register value, then timer counter will increment by once. So how prescaler counter is counting? It will count the incoming pulses coming from the crystal oscillator. Before the pulse count reaches timer counter, The prescaling is dividing of the clock pulse is happening prior to it, hence it is called as prescaler, which helps in enhancing the bandwidth of the time delay generation, which we are going to see now. So there is a 32-bit prescaler in LPC2148 microcontroller with 32-bit prescaler register as we discussed right now, PR, and there is a 32-bit prescaler counter which is PC, and timer has a 32-bit control register. So there is a timer control register, and timer has a 32-bit timer counter. Okay, so there is a timer counter is our 32-bit counter. So 32-bit timer counter with 32-bit prescaler. So it is 64-bit counter. Exactly speaking, it looks like 64-bit counter. Presence of prescaler has lot of convenience that we are going to experience in a lot in the future. Okay, so when prescaler register is loaded with the value, for example, FFFF means, so when the prescaler register value is loaded with 8 Fs means it is around 4 GB, which is equal to around 429 crore, 49 lakh, 67,296 counts. Okay, so when the timer is enabled, right, that means for every falling edge, prescaler counter starts from 0 and it counts up to prescaler register value. When it matches, then timer counter will increment by 1. After 429 crore, 49 lakh, 67,296 counts, so prescaler counter will overflow and then timer counter will increment once. Okay, so for one overflow of timer counter, it take around 429 core into 429 core pulses need to be counted. So very large amount of bandwidth of time delay can be achieved with the presence of prescaler, that we need to understand. We are supposed to see the registers with respect to the timers in a LPC2148 microcontroller. So there is a snapshot. Purposefully there is a snapshot because the snapshot was taken from the data sheet, which highlights the need for looking at the data sheet whenever we work with any microcontroller. In the data sheet, in the table 237, so all these 4 registers, that is timer counter register and timer counter and prescaler register and prescaler counter is being shown, and it is rewritable and the reset value is 0. And for timer 0, this is the prescaler register values and timer values. For timer 1, this is the timer counter syntax as well as its memory mapped register location in the addressable space. When you write a code, it starts with hash include LPC214x.h is our first line of code. And as usual, our void main direction register need to be initialized for blinking of the port. So direction registers are made as output port, right? As we all know. So these GPIO pins are configured as output port through IO0 direction registers. And here timer 0 prescaler register is used. So timer 0 prescaler register is loaded with the prescaler value of 6Fs. Okay, so prescaler value of 6F for our convenience. And timer 0 timer control register is loaded with 1. So if the timer 0 timer control is loaded with 1 means it starts the timer count. It is similar to TR0 equal to 1 in 8051 microcontroller, which will start the counter. Okay, so now the direction register is initialized. Why direction register is initialized? Because we are interested to blink the LED whenever the time happens. For that purpose, we have initialized the port 0 by making the direction register of port 0 as FFFF. So those port becomes output port, and the prescaler register and timer 0 is being initialized as shown here. So this is timer initialization and port 0 initialization, which has to happen only once, hence it is written inside the void main. So then while 1, so while timer 0 timer count value is less than or equal to 4 counts. So as long as it becomes 4, it will wait here. Then when the timer counter value exceeds 4, we are resetting the timer counter value. That means we are clearing the timer counter value, and then we are interested to toggle this port pin. Its syntax IO0 pin equal to 1's complement of IO0 pin. Okay, so that's all about this code. Main thing, if you want to concentrate here, is there is no delay routine which decrements the variable. By way of decrementing, we are not producing any time delay. Why? Because by way of decrementing means processor is loaded. Here, the processor is not much loaded. The processor is just waiting for timer 0 timer counter value only. It is not decrementing any job because the time delay requirement is satisfied by the timer through prescaler also. Here our objective is to look at how prescaler works. So let us examine this code by putting it in the Keil IDE. So you can see there is a registers and the code So whatever we have seen right now, those code is being written, and this is the timer register window, and this is the general purpose input output window. So this is the simulation window of the Keil IDE. The code LPC2148 void main and direction is kept as FFFF, and the timer is started, and the prescaler list value is loaded with FFFF, and the program inside the while loop is waiting until timer 0 timer counter value becoming 4, and when it becomes 4, T0PC is cleared, and then we are toggling the IO0 pin. So as you see, the program counter is pointing the fourth line, which is IO0 direction register. Earlier, the direction register is 0, but when we execute the fourth line by doing single step execution, so when you do the executing the fourth line, the direction register has become 1. So the port 0 has become output port now. Then timer 0 timer control register is set. So this is timer 0 timer control register, which is 0. So when you execute the fifth line, so the least significant bit is set as 1. So this will enable the timer. So after executing the fifth line, we can see the tick mark in the enable box. As you see, look at the screen, look at the cursor. So after executing the fifth line, so if you see here, when you do the single step execution, so the fifth line is executed, we can see the timer 0 timer counter value is made as 1, and the timer is enabled. So this 1 is to enable the timer to start counting. And this is the prescaler register. Earlier it was 0. Now the timer 0's prescaler register is loaded with 6 Fs. That is what that will happen by executing the sixth line. So I'm doing the single step execution. Now timer 0 prescaler register is loaded with 6 Fs, and the execution starts. Right now the execution starts. So let me do, I'm just doing the single step execution. So the prescaler counter started counting, right? Because the timer is enabled, prescaler counter started executing. Here what we have to observe is the prescaler counter starts from 0 and goes up to this value, 6 Fs. Whenever the prescaler counter value matches with the prescaler register value, the prescaler counter will become 0 and timer counter will increment by 1. Okay, so timer counter will increment by 1. Again, it will go from 0 up to the prescaler register value, and then again timer counter will increment by 2. That will happen. That is what we are going to see now when we run this code. Okay, so just let me run this code, and if you observe carefully, here you can see 1, 2, 3, 4, 5, 6, 7, 8 up to F. It will prescaler counter will count. So when it becomes F, that is all Fs, timer counter will become 1. Now EF. Now timer counter has become 1. Then again, it starts from 0 and goes up to FFFF 6 Fs. Then the prescaler counter value matches with the prescaler register value. Then timer counter will increment by 1, which is 2. Okay, so divide by 6 Fs. That is what the idea we need to understand. So whatever value that you want to divide, then we can use it here for our convenience. Okay, this value will be easy for us to simulate. That's why I have loaded this value where we can able to wait until it becomes 6 Fs. After that, we are able to visualize the timer counter is incrementing to 4 or something like that. We can able to understand very clearly. Okay, so it has become 4. Now you can see here after 4, right? When it is greater than 4, then it will toggle the pin, right? So now it is 4. After 4, it will become 0, and then let me see output pins are 0. Now it has become 1. Because output pin has toggled. That is what the code that we have written. So the output pin has toggled, and then again T0 TC is cleared, and then prescaler counter is repeating the same. Okay, so the prescaler is nothing but the divider. So divide by 1000, divide by 2000, divide by n number of values up to 0 to 439 crores. Any value that you fix up to that value, prescaler counter will count. So whenever the prescaler counter value matches with the prescaler register value, timer counter will increment, and prescaler register will also reset, and then it will start from 0. So that is visualized very clearly in this simulation. Okay, so here you can see the timer count has become 3, and it has become 9 A, B, C, D, E, F. When it crosses F, this will become 0, and the timer counter has reached 4. Now you see the output, right? Now if you see the output is 1. After this becomes FF, 4 will become 0, and then this will become 0. See, this has become 0, and 4 has also become 0 because the code was written only like this. If you see, when it is, as long as it is less than or equal to 0, it has to be in the while loop. When it is greater than 0, clearing the timer counter and toggling the pin is the thing which we are supposed to monitor here with respect to this thing. So now we have able to understand, we can able to understand the use of prescaler register and prescaler counter in the timer, which helps us to design, or which help us to program, or which is to plan n number of time delays by using this prescaler register and this timer counter value. So that is what we have understood by simulating this particular code in this example. Okay. So now let us look at some more better features of this LPC2148 microcontroller. So let us all play a match with a catch. Okay, let us assume there is a timer or counter which starts from 0, goes up to 255 if it is 8-bit timer. Starts from 0, goes up to 63,536 if it is a 16-bit timer. Starts from 0, it goes up to 429 core if it is a 32-bit timer. Let us assume there is one more register called compare register. If we have a compare register, and if we load some value in the compare register, okay, something like how we have loaded some value in the prescaler register. Now you can relate the compare register with prescaler register, and this timer value is nothing but the prescaler count register. So what happens whenever the timer value, prescaler counter value is matches the prescaler register value, so it increments the timer counter value. Similarly, so in the compare register, if you fix some value, so the timer will start counting. So, and the timer value is always compared with the compare register value. So whenever the timer value is equal to the compare register value, it produces a transition in the pin. Okay, produces a transition in the pin means if the pin is already 1, the pin will become 0. If the pin is already 0, the pin will become 1. So like that we can program. So this feature of this compare register or compare match feature of this timer is very much helpful in producing pulse width modulation for a particular application. So for any linear control applications or non-linear control applications, PWMs are most widely used. So the PWM is generated with the help of compare register, compare match register. Okay, so there is a compare match register which is called as match, which is what I was mentioning. Whenever the timer value matches with the compare register value, that means that is what the within the circuit is shown as equal to, then it produces a transition in the pin. So as you know very well, timer starts from 0 and counts up to its maximum value and overflows. After overflow, it becomes 0, and this process will continue, which resembles like a sawtooth waveform, as we all know, as you see in the screen. So the x-axis is time axis, y-axis is the count value. So if it is an 8-bit counter, it starts from 0, it goes up to 255. So this is the count max. When it reaches 255, it overflows. When it overflows, it becomes 0. From 0 again, it will start count from 0 up to 255. So when it reaches 255, it becomes 0. Similarly, if it is a 16-bit, starts from 0, goes up to 63,500. So you can say this is one period. Okay, one sawtooth is one period. Say for example, if it is an 8-bit microcontroller with 8-bit timer or counter means, with respect to our understanding, when one count equal to 1 microsecond means, it will start at 0, goes up to 255. So after 255 count, it will overflow. So it the count value comes from 255 to 0. So what is the time duration? Time duration here it is 255 microsecond. Something like that in terms. So the one period of the pulse, you can say it is 255 microsecond. Something like that you can understand by looking at this screen. So this is how timer counter starts. Timer starts from 0, goes up to maximum. When it reaches maximum, becomes 0. Then starts from 0, goes up to the maximum. Maximum 0. When it becomes maximum, it becomes 0. It looks like a sawtooth waveform. So it takes some time. The time is 256 microsecond with respect to our 8-bit understanding. Okay. Now, to produce a pulse width modulation, waveform, so this timer value should be compared with some other register, which is nothing but your compare match register. Okay, so something like this. You can see the compare register. Let us say it is 255 count. Let us say it is 255 count. So I have loaded the compare register value with say 100. So the compare register value is loaded with 100. So timer starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 40, 60, 80, 90, 100. Now the timer value becomes 100 and the compare register value is also 100. So there is a match between the timer value and the compare register value. If there is a match, it has to produce a transition in the pin. So earlier the pin was in logic 1 state, means the pin will become 0. whenever there is a match. After that, the timer will keep on counting. Timer will go up to its maximum, which is 255 in our case. Then after it reaches maximum, becomes 0. So whenever it resets from the maximum to 0, the pin also will reset to its initial state, which is 1. So it remains in 1 until the timer value reaches or matches with the compare register value. Whenever it matches the compare register value, as you see here, whenever it matches with the compare register value, it produces a transition in the pin. So again, the timer will count and the timer will reaches maximum. Whenever it reaches maximum, it will reset. So when it becomes reset means it will start from 0. So the pin also will reset to its original state, which is logic 1. And the timer will start count, and the third time there is a match. Third time there is a match between the timer value and the compare register value. So whenever there is a match, it produces a transition in the pin. Okay, so we are getting the pulses like this, which is pulse width modulated output, which is used for linear control in most of the applications. Okay, so by varying the compare register value to some other value, so let us assume this is 100, means the pulse width is like this. Now let us assume I have changed the compare register value as 200. Instead of 1, the compare register value I will change it as 200, something like this. Okay, so the same process continues, right? So timer starts at 0, it goes up to 200. When it reaches 200, then what happens? When the count reaches 200, the timer value matches with the compare register value. Then it produces a transition in the pin. So earlier the pin was in logic 1 state. Whenever there is a match, it produces a transition from 1 to 0 and remains in 0 until the timer overflows. When timer overflows, it resets. When it resets again, the pin goes back to its original state and retains in its 1 state until the next match. So again, its timer starts from 0, goes up to 255. In between, there is a 200 value. Assuming this compare register value is 200. So when it reaches 200, it matches with the compare register value. So whenever there is a match, it produces a transition in the pin. Okay. So and this process repeats, and every time the timer value matches with the compare register value, it produces a transition in the pin. Every time the timer overflows, the pin resets to its original state. So when you look at the screen, so the red value produces the red pulse with minimum pulse width. The green value produces the green pulse with maximum pulse width. So by changing the compare register values, like these two examples, we can adjust the width of the pulse. Okay. So if you observe carefully, the pulse width duration is 255 microsecond means. So in 1 millisecond, 4 pulses will come. So 4,000 such pulses will come inside as the output of the pin, which is more than sufficient for any linear controls or any intensity control or speed control or volume control of our n number of applications, as we are now doing. Okay, so the compare match register present inside the microcontroller is timer is another feature which helps us to produce pulse width modulation with respect to LPC2148 register. So there are 4 32-bit match registers which allow the continuous operation with optional interrupt generation and match. Even after match, you can continue the operation. That is one option. Stop the timer on match with optional interrupt generation. So whenever there is a match, there is a possibility for us to stop the timer. Or whenever there is a match, there is a possibility for us to reset the timer. Along with that, we can have the control over the pin. That pin I was calling it as a PWM pin. So whenever there is a match, set that pin as low. Whenever there is a match, set that pin as high. Or whenever there is a match, toggle that pin. Something like that we can do. Or whenever there is a match, we can do nothing on match. Something like that we can say. So these are all the facilities or features available in the LPC2148 timers. So based on the application requirement, the design engineers can make use of these features. Okay, so that is the idea here. Okay, so there is something like match, and similarly there is something like capture. So there is a register called the capture register. Similar to the compare register, there is a register called the capture register. Sometimes it is called the snapshot register also, which is again quite interesting. So if through the compare register, if you are able to generate pulse width modulation, means through capture register, it is possible for us to measure the PWM. Okay, anyway, we have to measure the PWM. So PWM has to be measured means what? The duty cycle need to be measured. The measuring has to happen in microseconds and milliseconds. Again, to measure the some activity which is happening in microsecond, millisecond means you have to make use of timer. That too, capture registers will fulfill that requirement. Okay, how this works? Let us quickly refresh this. So there is something like a capture register. Timer counter value is connected to the capture register through a tri-state buffer. So because it is a tri-state buffer, we have to enable this tri-state buffer. Okay, so whenever we enable this tri-state buffer, at that moment, what is the timer counter value that will be captured by this capture register. That is why it is named as capture register. So when the enable signal will come, so whenever there is a transition in the pin, the enable pin will, the tri-state buffer will be enabled. So the timer counter value will be captured by the capture register. It's very interesting, right? Okay. So in a compare match, the timer value is compared with the compare register value. Whenever there is a match, it produces a transition in the pin. So that is means it is output. But when you look at the capture register, whenever there is a transition in the pin, that enables the tri-state buffer. By the time of transition, what value is there in the timer, that value will be captured by the capture register. With that capture register value, we can able to measure the on time of the pulse or off time of the pulse, which we are going to see it with an example, right? So this is the pulse width waveforms that we have created with the help of match register. So during the rising time, what is the timer value which we have to identify, right? If you look at the screen, so there is a point. So by the time of rising, right? Here there is a transition from 0 to 1. During this transition from 0 to 1, what value is there in the timer? Say for example, the timer value is 0. So that 0 is captured by the capture register 1. Okay. So then again there is a transition from 1 to 0. So during this transition, if we capture this timer value, let us say it is 100, say for example, capture register 2 value minus capture register 1 value, very easily can find the on time of the pulse, which is helping us to find out the duty cycle of the pulse, which can be represented in percentage. In our mobile phone, when you look at the light intensity, right, when the screen intensity, we are able to see 100%, 50%, 20% means that is the duty cycle, which is observed only with the help of the capture registers inside our Qualcomm Snapdragon microcontroller sitting inside our mobile phones. So similarly, we are supposed to find out the period of the pulse. Period of the pulse means finding the capturing the time interval between two consecutive rising edges, as you see here, two consecutive rising edge. During the rising edge here and another rising edge is happening here. So time taken between these two rising edges means it will help us to find out the total period. So within this period, how much time it is on, something that we can able to measure. So measuring the period is very much useful in measuring the frequency of the pulses. Yes or no? 1 by period equal to frequency. Okay. So to measure the frequency, to measure the duty cycle, the capture registers are very much helpful. So that will be very much useful. In the later classes, we will be celebrating this in much better way with few examples. Right now, your focus is to understand the timer. So the timers have capture registers and match registers, where the match registers are helpful in producing the PWM and the capture registers are helpful in producing the measuring the PWM. That means measuring the duty cycle as well as measuring the period of the pulses, as we discussed rightly in this example. Okay. So with respect to LPC2148, so there are 4 32-bit capture channels per timer. So there are 2 timers. So timer 0 has 4 32-bit capture channel, which can take a snapshot of the timer value when an input signal transitions. That is what we have discussed. So capture event may also optionally generate an interrupt. So we can able to generate the interrupt also. So now you can understand. So from the first block, here you can see the first slide you have seen some block diagram. In the timer block you have seen something, right? I want to show this now. So here you can see 4 capture. Okay, you can see now you can able to understand this. So timer 0, timer 1, timer operation we know very well. But the capture compare, this capture, now you got the meaning for the capture compare, where capture means it is coming as an input. So whenever there is a transition, it acts as an enable to the tri-state buffer. So the timer values are captured by the capture register, which helps us to find out the on time or the period of the pulse. That is why it is input. So there are 4 capture registers. So 4 capture pins with respect to LPC2148 microcontroller for timer 0. And there are 4 capture pins with respect to timer 1 with respect to LPC2148 microcontroller. Similarly, there is a match register. So whenever the timer value matches with the match register, it produces a transition in the pin. That's why the arrow mark comes out. Okay, so it generates PWM, it measures PWM. That's why. Okay, because there are two timers, so match 0 and match 1. With respect to LPC2148 microcontroller application series, interval timer for counting the interval events. Counting the interval means what? Time interval between the pulses can be measured by using capture register, and pulse with demodulator via capture inputs. So we can demodulate the pulse. Demodulate means we can measure the on time of the pulse with the help of capture registers and free running timers, something like this. In chapter in the datasheet is features. Now you can understand a 32-bit timer or counter with a programmable 32-bit prescaler. Now you're very clear about timer, we are very clear about prescaler. Fantastic. It can be used as a counter or a timer, that we all know very well. Up to 4 32-bit capture channels per timer that can take a snapshot of the timer value when an input signal transitions. The capture event may also optionally generate an interrupt. That is what we have discussed right now. And 4 32-bit match registers that allow continuous operation with optional interrupt generation, stop timer on match, and reset timer on match with optional interrupt generation, which is what discussed right now. So up to 4 external outputs corresponding to the match registers with the following capabilities: set low on match, set high on match, toggle on match, and do nothing on match. That is what is being discussed in the as a features. Now you are very clear about all the features which was demonstrated, and this is the application which was shown in the slide also. Okay. So rest of the thing you can look at the 15th chapter on the data sheet, which helps us to understand much better about the timers in LPC2148 microcontroller, which is an ARM-based microcontroller. So this capture modules are very much useful in finding the speed of the vehicle, right? If there is a speedometer in a car, speedometer in a bike, speedometer in a thing means you say that 20 kilometer per hour or 40 kilometer per hour or 80 kilometer per hour. If there is a digital display, so those digital displays are happening only by measuring the pulses coming from the wheel speed sensor. Okay. All the speedometers, all the RPM of a motor speed control, and wherever there is a speed measurement or tachometer, whatever you call, all are measuring the transition between the rising edge and falling edge, which is on time. Based on that, they will measure the period, and by measuring the period, they will find out the frequency, and they'll say this is the RPM of the motor, or this is the RPM of wheel. Based on that, they will compute the speed of the vehicle, and you can say your vehicle is traveling in 80 km per hour or 90 km per hour. Okay, so when you're being an electronics and communication engineer, if you are appointed in Robert Bosch and you are interested in making the display, which is called as instrument cluster, doing that instrument cluster, you are supposed to design a speedometer. Means you have to write a program by looking at the wheel speed sensor, and those wheel speed sensors input are given to the capture module. So whenever there is a transition, you have to capture that, and capture value 2 minus capture value 1, you will get the on time. So based on that, you can able to find out the frequency. Based on that, you can able to compute the speed of the vehicle, and then by doing the necessary code conversion, you can send it to the 7-segment display, because all the sophisticated digital displays in a car is also having only 7-segment display to display the speedometer and speedometers, odometers, wherever there is a display. So this can be used in a more beautiful way. So thank you.